Hello, everyone, and thank you very much to the organizers for inviting me to give this talk. My name is Emilie Hertig. I am a third-year PhD student at the University of Cambridge, and today I will present the implementation and testing of a component separation pipeline, including B-mode delensing for the Simons Observatory. As some of you may know, the Simons Observatory, or SO for short, is a ground-based CMB experiment which has just started collecting data in this beautiful site of Cerro Tocco in Chile. One of SO's main science goals is the study of cosmic inflation, the very violent phase of accelerated expansion, which we think happened in the first fraction of a second after the birth of our universe. Inflation is considered to be a crucial time which sets the initial conditions for the properties and the structure in the universe that we know today. So understanding the quantum fields and the potentials at play is of significant interest for both cosmology and high-energy physics. The richest source of information on the primordial universe is the cosmic microwave background, or CMB, so this is where we are looking for the signatures of inflation. The temperature of the CMB has been mapped with near optimal precision by Planck. To learn more, we need now to focus on the polarization patterns resulting from Thomson scattering in the presence of temperature anisotropies. An important prediction of all inflation models is the creation of density perturbations and primordial gravitational waves through the amplification of quantum fluctuations to macroscopic scales. While scalar perturbations can only produce parity-even E-modes, tensor perturbations are geometrically more complex and are also able to generate parity-odd B-modes. Detecting such B-modes would be a major breakthrough, as it would allow to determine the tensor-to-scalar ratio R, which is directly related to the energy scale of inflation. The current upper bound shown here has already allowed to rule out several of the simplest classes of inflation models. Improving upon these constraints is a tremendous observational challenge. The first reason is that the primordial B-modes are intrinsically very faint, with their predicted power spectrum being multiple orders of magnitude lower than that of the E-mode and temperature anisotropies we have already measured. The second reason is that our own galaxy contains bright sources of polarized light, in particular thermal dust emission and synchrotron radiation. As you can see on this plot, the resulting B-modes are significantly larger than the primordial signal. The third challenge comes from weak gravitational lensing. CMB photons have to travel through large-scale structure in order to reach us. Along the way, their path gets deflected, and the subsequent remapping of polarization and isotropies causes initially pure E-modes to pick up a B-mode component that wasn't here at first. These lensing B-modes are given by a weighted convolution of the original E-modes and the lensing convergence kappa, and their presence affects our uncertainties on R. For SO and future experiments, the instrumental noise level, NL, will be low enough that the lensing term is becoming significant in comparison and needs to be mitigated. This is the process we call delensing. It consists of building a model or template of the lensing B-modes that we can then subtract from the data. The factor F here indicates that lensing induces a coupling between different multiples. This means that although primordial B-modes peak at low Ls, building an accurate template over these scales requires high-resolution measurements of the E-modes and lensing convergence estimates. In SO's case, we will obtain both of these from this Large Aperture Telescope, or LAT. The three Small Aperture Telescopes, or SATs, will focus on a significantly smaller area of the sky in order to target large-scale B-modes with unprecedented sensitivity. By observing in 6 frequency bands, they will allow us to disentangle galactic foreground emissions from the CMB, thanks to their distinct spectral energy distributions, or SEDs. The two low-frequency channels will mainly constrain synchrotron radiation, while the high-frequency bands will provide information on dust, and the mid-frequency channels will be the most sensitive to the CMB signal. With this nominal design, SO aims to detect or rule out a value of R above 0.01 at the 3 sigma level. Let's now see how we can perform delensing using data from the LAT. We start by reconstructing the lensing convergence field internally. When cross-correlating two lensed fields, which can be either a temperature or polarization, we get a diagonal term, which just corresponds to the unlensed power spectrum. And the lensing deflections also contribute an additional off-diagonal term. which depends on the Delensing convergence kappa. This means that if we combine two observed lens fields with a conveniently chosen prefactor, we can cancel out the diagonal term, also cancel out this small g, and we get an estimate of the convergence kappa, which we call a quadratic estimator. In this work, we will use the following 4 pairs of fields. We don't use TB because the signal-to-noise ratio is quite low. And as you can see on this plot, this technique works really well on large scale, but becomes noise-dominated on smaller scales, where the correlation with the true lensing convergence drops. To improve the overall correlation, we combine the internal estimator with external large-scale structure tracers. Here, for example, we use simulated tracers based on LSST forecasts and Planck CIB maps. The final lensing convergence estimator is given by a weighted sum of internal and external tracers. The weights are optimized at each multiple to maximize the correlation between our estimator and the true convergence. So after obtaining this kappa estimator, we also extract high-resolution E-modes from the lat maps and apply a Wiener filter to mitigate instrumental noise. Finally, we can then compute the convolution I was showing earlier to obtain the Delensing B-mode template. Here's an example of a lensing template we obtained after running this stage of the pipeline on lat-like simulations with realistic inhomogeneous noise. You can see the original lensing B-modes in our input simulation here on top. And this is the same area in the corresponding lensing template. The correlation between the two is obviously visible. And when subtracting this template from the input B-modes, the fraction of power that remains is about 35%. This means we are able to remove 65% of the lensing B-modes with this approach. That's a considerable amount. Now moving on to the component separation stage. Here's a summary of the power spectrum-based foreground cleaning pipeline developed for SO. First, we compress the information contained in the multifrequency set maps into a set of cross spectra. We obtain their covariance from simulations and perform a Bayesian likelihood analysis to obtain probability distributions for the parameters of our theoretical model. For the CMB part of our model, we use theoretical power spectra from CAMB and just have R as a free parameter. The intensity of the foregrounds is scaled in frequency by the spectral energy distribution, or SED, this INU function here. In the simplest cases, it is assumed to be uniform in space. And we also model the foreground power spectra as power laws. Now, if the foregrounds are more complex and the SEDs actually vary in space, we use the moment expansion method, where we expand the SED to second order and then propagate this to the power spectrum level. This means that for each foreground component, we then need 2 more fit parameters included in our model. Now, to include Delensing, we essentially consider the Delensing template as an extra input map, just like another frequency channel. We compute the additional power spectra by cross-correlating it with itself and with the set B-modes. We get the model and covariance for this spectra from the average of simulations. And the likelihood is extended to include all these as additional power spectra. And finally, MCMC sampling leads to tighter constraints on R. One thing you might wonder then is whether considering the Delensing template as a separate input leads to similar constraints on R as subtracting it from the set data at the map level. To check that, we look into this well-known expression for the Fisher information, which is directly related to sigma R. We consider just one set frequency channel for simplicity. In the map-based case, this is what enters our likelihood: the original set B-modes in the map, then the noise contribution minus the B-mode template. Now we can actually simplify the delensed power spectrum further. Indeed, when we use Wiener filtered E-modes and the optimized combined lensing convergence tracer that I was showing earlier, the auto spectrum of the template is equal to its cross spectrum with the true B-modes. The figure here shows that we verified this for our simulations, and you can refer to the paper on arXiv for the mathematical proof of this if you're interested in that. So using this result, here's the Fisher information in this map-based case. Now, if we take the template as a separate input, these are the set of cross spectra. We use the same technique to simplify this matrix, substitute it into the matrix expression now for the Fisher information, and we get actually the same result as in the map-based case. So those two methods are indeed equivalent, and the advantage of the cross-spectral one is that some effects such as beam deconvolution and filtering can be dealt with much more easily. As the set has strongly inhomogeneous noise properties, one essential aspect of this cross-spectral technique is the weighting applied to each pixel in the input maps when computing power spectra. We determine the optimal weights by minimizing the variance on the power spectrum estimators for a delensed and foreground cleaned map. The term on the left here represents the lensing residual power. So A lens depends on the delensing efficiency of our template. For the multiple range considered in our analysis, instrumental noise is approximately white. So the second term is the effective white noise level modulated by the number of hits. Here you can see the latest version of the hit count maps for the SO, LATs, and SATs, and I used the set hit counts put into this formula to generate the optimal weights on the overlap region between the SAT and LAT survey areas, as you can see here. And this is the mask that we will use to compute our power spectra in the pipeline. So now we test this component separation stage on simulations. These simulations contain the lensed CMB signal convolved with the correct beams for each channel, SAT-like inhomogeneous noise, and non-Gaussian synchrotron and dust emission maps. These are informed by past observations. For now, we keep the spectral energy distributions constant in space, but later on we will also test more complex foreground models. These two plots illustrate what the power spectra that go into the likelihood look like. So the top one is an example of SAT channel autospectrum, where the foreground and instrumental noise contributions are visible at large and small scales respectively. And as expected, these effects do not appear in the cross spectra involving the lensing template. Here are the posterior distributions obtained for one input simulation containing these simple foregrounds. These three parameters here are the SED index, power spectrum amplitude, and exponent for synchrotron radiation. Same thing here for the dusts. This epsilon ds parameterizes the correlation between dust and synchrotron. And of course, the most important parameter for us is the tensor-to-scalar ratio R. So as you can see on this zoomed in plot, delensing leads the error on R to decrease by nearly 40%. And as a cross-check, we also compare the value of sigma R that we get after delensing to the uncertainty obtained for an input simulation in which the lensing B modes have been artificially reduced by 65%. We observe an excellent agreement, which verifies the proper functioning of the pipeline first, but also the result I was mentioning before about the equivalence between map-based and cross-spectral delensing. We then compared our optimal pixel weight to the other weighting schemes used in previous papers. As expected, weighting pixels uniformly over the survey area, that's the dotted line, is clearly suboptimal. The dashed lines represent weights that only account for the inverse noise variance in each pixel, so just the instrumental noise, not the lensing residuals. The results with this scheme aren't very different from ours, but the optimal weights derived earlier do still yield the tightest constraints. And furthermore, the difference between our optimal weights and the inverse noise variance ones will only increase in the future as instrumental noise levels go down. The lensing residuals become comparatively more important. So this technique will actually have more of an advantage in the future. Now, all plots so far were made for just one realization. Here's now the main result of the paper, showing summary statistics for 4 different sets of input simulations. Each time we used 100 different simulations and averaged both the best fit estimate of R and the statistical uncertainty. So for the first 3 data points here, the input maps were generated with R equals 0, and we included increasingly complex foregrounds. So the D0S0 has the spatially constant spectral energy distributions. D1S1 and DMSM are PySM3 foreground models that contain realistic spatial variations of the SEDs. So in these two cases, the inclusion of the 4 extra parameters for the moment expansion leads to larger error bars. And the improvement related to delensing is a bit more modest, but it is still significant. We also tested a set of simulations with non-zero R, which was successfully detected. And what we notice in all cases is that delensing leads to a reduction in the size of our error bars by about 30 to 40%, depending on foreground complexity. And in all cases, even the most complex one, we achieve SO's target precision after delensing and even surpass it. So in summary, what we've done is included a multi-tracer lensing template as an extra channel into our power spectrum-based likelihood, optimized the pixel weights to minimize the variance on these power spectra, and testing our method on 3 increasingly complex foreground models, we managed to improve sigma R with delensing by 30 to 40%, which is a significant and encouraging improvement. These results are the first realistic performance forecast for the Simons Observatory, including delensing. And here are some future prospects. Of course, now that data is starting to become available, the obvious next step for this work will be application to early SO measurements. As the Large Aperture Telescope will not be in operation this year, it will start in 2025. What I have started to work on is building a lensing template from other datasets, so the ACT-DR6 lensing map, unwise galaxy samples, as well as the Planck Genilk CIB map. So here you can see a preliminary result showing the correlation coefficient between our combined tracer using those datasets and the true lensing convergence. And the hope is to use the lensing template built from this combined tracer and ACT or Planck E-modes to delens early SOB modes in the coming months. And just to finish, I wanted to note that all the results I showed in this talk were obtained assuming the nominal SO design with 3 small aperture telescopes. However, we now know that the observatory will be extended by adding 3 additional sets around 2026. So this will, of course, reduce instrumental noise further, and the lensing variance will become a more significant limitation in comparison. So this really highlights the importance of delensing, which is truly becoming an essential step towards reaching the full potential of current and future primordial gravitational wave searches. I look forward to answering all of your questions during the live sessions, and thank you very much for your attention.